Hello all, welcome to the first video for section 1.7 on the linear independence. Given a matrix A with columns A1, A2 up through AN, we saw last time the corresponding homogeneous matrix equation is AX is equal to 0, which always has the solution, always has that X is equal to 0 as a solution. And sort of a natural question to ask is X equal to 0 the only solution? To this homogeneous equation. It'll depend on A, certainly. Let's move this up a little bit, give ourselves some more room. There we go. Okay, it's supposed to sort of motivate this next definition. So a set of vectors v1, v2 up through vp in Rn is linearly independent if what? If the vector equation x1 v1 plus x2 v2 all the way up to xp vp. Oops, x isn't the xp vp is equal to 0. If the equation only has the trivial solution x is equal to 0, has only the trivial solution. Yeah, where each of these components x1, x2 up through xp is equal to 0. So if these vectors are linearly independent, the only way to get the sum to the 0 vector is if all the basically if you kill each vector with the number 0 in front of it. Otherwise we could say that v1 through vp are linearly dependent. So let's be a little more explicit about that. Yeah, these vectors are linearly dependent. If what? If there are real numbers C1, C2 up through CP, not all 0, with the property that C1, V1 plus C2, V2 plus all the way up to CP, VP is equal to the 0 vector. So the big difference here is that we're allowing some real numbers, some of which aren't 0. Here we're saying the only way we can get the sum to be equal to 0 is if all of the x's are 0. That's linearly independent. Linearly dependent is we can find some non-zero real numbers C1 through CP that make this true. Okay, and this is called the linear dependence relation. Okay, so let's take a look at an example and make this more concrete. So let's determine if these given vectors 1, 2, 3, 3, 4, -1 is what I want. It doesn't really look like that. 3, 4, -1, 1, 0, -7. We're going to determine if they're linearly independent or linearly dependent. Okay, and so once again, we've been given some new vocabulary, but it's really going to boil down to just solving systems of equations. So we want to solve, C1, V1 plus C2, V2 plus C3, V3 is equal to 0. So once again, all we're going to do is collect the vectors V into a matrix, collect the scalar C into a vector, and really just solving AC is equal to 0. And we know that solutions to that matrix equation come down to solutions to a system of linear equations. So let's find the augmented matrix for that system. Okay, so what we're doing is, making the matrix out of these vectors and then using zeros for our augmented column. So we're looking at the augmented matrix 1, 2, 3, 3, 4, -1, 1, 0, 7, 0, 0, 0. Okay, and we'll do what we always do. We'll take the second row and subtract twice the first row. We'll take the third row, subtract 3 times the first row. Okay, so our first row is unchanged. 2 plus negative 2 times 1 is 0. 4 plus negative 2 times 3 is negative 2. 0 plus negative 2 times 1 is negative 2, and 0, whatever, 0. Okay. 3 plus negative 3 times 1 is 0. Negative 1 plus negative 3 times 3 is negative 10. I'm sorry, this is supposed to be negative 7. Right? Negative 7. All right. Negative 7 plus negative 3 times 1 is negative 10 again. And then 0, yeah, 0. All right. And let's continue to row reduce. Oh yeah, okay. So what should we do? It looks like we can take negative 1/2 times row 2, leave everything else the same for a sec. 0, 1, 1, 0, 0, negative 10, negative 10, 0. And then we can do row 3 minus, or maybe plus 10 row 2. And get 1, 3, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0. Okay. Now what? Final thing we want to do is probably row 1 minus 3 row 2. So 1, 0. 1 minus 3 is minus 2, 0, 0, 1, 1, 0, 0, 0, 0, 0. Okay. And this is yeah, completely reduced. So we're getting now x1 minus 2x3 is 0, and also x2 plus x3 is 0. Or in other words, x1 is 2x3, x2 is negative x3, x3 is free. Okay. So in particular, we're getting more than just the trivial solution, right? We don't need C1, C2, C3 to be all 0. We can grab x3 to be equal to 1, x1 then to be equal to 2, and x2 to be negative 1. And that would give a solution. Or we could take x3 to be 10, and then x1 is 20, and then x3 is negative 10. Lots of solutions floating around for us out there. So we can take, for example, 2, negative 1, 1 for our solution. And we get twice v1 minus v2 plus v3 is apparently equal to the 0 vector. And if you don't believe me, I encourage you to, pause the video and double check that if you really do take twice v1 and subtract v2 and add v3, you get back 0. The 0 vector. Okay. Boom. Okay, and we can connect this, sort of our connection to matrices. Yeah, so the columns of A are linearly independent. If and only if our homogeneous equation has only the trivial solution. It's only the trivial solution. Okay, so we might reasonably ask, yeah, are the columns of the matrix 1, 0, 1, 0, 1, 1, 2, 3, 1 linearly independent? Okay, and again, it's a little bit of vocab. We know this just amounts to solving the homogeneous equation and figuring out if there are non-trivial solutions to where our x1, x2, and x3 aren't all 0. Okay, so let's take a look. So we've got to reduce. Oops. Reduce the augmented matrix. 1, 0, 1, 0, 1, 1, 2, 3, 1, 0, 0, 0. And what do we do? Let's take row 3 and subtract row 1 first. 1, 0, 2, 0, 0, 1, 3. Oop. And then 1 minus 1 is 0. 1 minus 0 is 1. 1 minus 2 is negative 1. 0 minus 0 is 0. Okay. Do we need to go further? Yeah, we need to figure out at least how many pivots we have. Okay, so let's go a little further still. If we do row 3 now minus row 2, 1, 0, 2, 0, 0, 1, 3, 0, 0, 0, minus 4, 0. Okay, and now we can see we've got 3 pivots, which I think is as far as we need to get to. So by our theorem 2, 3 pivots means no free variables. So which means so our system has at most one solution. So it could, according to theorem 2, it could have no solutions or one solution. But we know it can't have no solutions. We know that every homogeneous equation has at least one solution, has at least the trivial solution. So all our theorem 2 says is that since we've got 3 pivots, there are no free variables, and we can't have an infinite number of solutions. So it's either none or one, but we know it can't be none because we know the trivial solution is floating around. And so by process of elimination, there must only be the trivial solution. So we have one solution already. The trivial solution. So if there's only the trivial solution to our homogeneous equation, that means that indeed the columns of A are linearly independent. Yeah. So the columns of A are linearly independent. The only way you combine them to get the 0 vector is if you do the silly thing of doing 0 times the first one plus 0 times the second plus 0 times the third. Okay. I'll see y'all in a sec for the next video from section 1.7.